Have you ever looked up at the night sky? Out there, scattered across an impossibly vast canvas, are billions and billions of stars. These are places where the normal rules of the universe seem to completely break down. These are the universe's ultimate mystery, and we call them black holes. Imagine a place where gravity is so strong that nothing, not even light itself, can escape its grasp. It's like a cosmic waterfall with no bottom, where the river of space-time flows into a single, infinitesimally small point. Or are they simply the final dramatic endpoint for the universe's biggest stars? They are the universe's ultimate recycling plants, the graveyards of stars, and possibly the seeds from which entire galaxies grow. So get comfortable, because we are about to journey to the edge of reality and stare into the heart of a black hole. Now, you might be thinking, if nothing can escape from a black hole, not even light, then how on earth do we know they are even there? It's a brilliant question, and it gets right to the heart of the challenge facing astronomers. You can't just point a telescope at a black hole and expect to see it. It would be like trying to spot a piece of coal in a dark cellar with the lights turned off. By their very nature, they are invisible, so scientists have to be clever. They have to become cosmic detectives, looking for the clues and the telltale signs that these monsters leave behind in their cosmic neighborhoods. Instead of looking for the black hole itself, astronomers look for its effects on the space and the matter around it. Imagine a drain in a bathtub. You can't see the whole of the drain itself when it's covered with water, but you can see the water swirling around it, faster and faster as it gets closer to the center. It's the same with a black hole. We can see stars orbiting what looks like empty space, moving at incredible speeds. We can detect superheated gas and dust, called an accretion disk, swirling around the black hole's edge, glowing fiercely with X-rays before it takes its final plunge into darkness. These are the fingerprints the black hole leaves on its surroundings. This is not just theoretical guesswork either. We have seen these effects with our own eyes, or rather, with the eyes of our most powerful telescopes. We have seen stars wobbling in their orbits, tugged by the immense gravity of an unseen partner. In some extreme cases, we have even witnessed a star straying too close to a black hole and being torn to shreds by its immense tidal forces. This cosmic demolition derby, known as a tidal disruption event, releases a massive flare of energy that we can detect from millions of light years away, another clear sign that a hungry black hole is lurking nearby. And in one of humanity's greatest scientific achievements, we have even managed to take a picture, not of the black hole itself, but of its shadow. Using a global network of radio telescopes working together as one Earth-sized observatory, the Event Horizon Telescope project captured an image of the supermassive black hole at the heart of the M87 galaxy. It showed a dark central region, the point of no return, surrounded by a blazing ring of light from superheated gas. We are no longer just guessing, we are directly observing the edge of the abyss, proving that these incredible objects are very, very real. We know black holes exist, but where do they come from? They are the final chapter in the life story of massive stars. To understand how a black hole is born, we need to understand how a star lives and dies. It is a tale of balance, collapse, and spectacular cosmic fireworks. Think of a normal star, like our own sun. For billions of years, it exists in a state of perfect equilibrium. Gravity pulls in and fusion pushes out. But for stars that are much, much bigger, the story is far more dramatic. This triggers an explosion of unimaginable power, a supernova, and in that moment, a new black hole is born. Let's talk about black holes. A black hole is a place in space where gravity has gone completely off the rails. An enormous amount of matter has been squashed into an impossibly tiny space. This gives a black hole its inescapable gravity. It creates a one-way door in the universe. Anything that gets too close, even light itself, is pulled in. Once you cross that threshold, there's no turning back. Think of space-time as a stretchy rubber sheet. A black hole punches a hole right through it, creating a bottomless pit. It's a trap set by gravity itself. We call it the Singularity. At the heart of every black hole lies the Singularity. This is the bit that really messes with our minds. A singularity is what you get when you crush a massive star's core down to a point with zero volume. The laws of physics, as we understand them, stop working at this point. It's science's way of saying, we don't really know what's going on here. It is the ultimate endpoint of gravitational collapse. Some physicists wonder if a true singularity can actually exist. They suspect that a complete theory of quantum gravity will tell us a different story. When we talk about a black hole, we are really talking about two main parts: the singularity at the center and the boundary surrounding it. This crucial boundary has a very famous name, the event horizon. The event horizon defines a black hole, separating it from the universe. It's a horizon in space-time. Any event inside is trapped forever. No signals can escape. Black holes are black because the event horizon traps all light. The horizon's size depends on the black hole's mass. More mass equals a larger horizon. Imagine flying towards a black hole. The invisible event horizon has no physical barrier. Cross it, and your fate is sealed. There's no return. Inside, space-time flows inward faster than light. Escape is impossible. The event horizon, the cosmos's ultimate one-way membrane. We've used the analogy of a rubber sheet to understand gravity. Let's dive deeper into warped space-time. It's one of the most profound insights from Albert Einstein's theory of general relativity. Space and time are woven together into space-time. Massive objects tell space-time how to curve, and the curvature of space-time tells objects how to move. This is the essence of gravity. A black hole represents the most extreme curvature of space-time possible. One of the most famous effects is called gravitational lensing. The intense gravity of the black hole bends the path of light. This warping of space-time also affects the flow of time itself, known as gravitational time dilation. The stronger the gravity, the slower time passes. A black hole takes this effect to its absolute extreme, fundamentally twisting our notions of space, time, and reality. We've explored black holes. Now, let's rewind to their fiery birth in stellar nurseries. These vast, cold clouds of gas and dust float between stars. Within these clouds, gravity slowly pulls gas and dust together. Over millions of years, clumps grow denser, pulling in more hydrogen. The core heats up, forming a protostar. For a star to be born, nuclear fusion must ignite in its core. Hydrogen atoms fuse to create helium, releasing tremendous energy. A star is born, shining brightly. The size depends on the initial clump. Massive clumps create blue supergiants. These giants live fast and die young, becoming black holes. Once a star has ignited its nuclear furnace, it enters the main stable phase of its life. For billions of years, in the case of a star like our Sun, or for just a few million years for a massive supergiant, it exists in a state of beautiful equilibrium. It's a constant, epic battle between two of the universe's most powerful forces. On one side, you have the relentless, crushing force of the star's own gravity. This immense gravitational pull is constantly trying to squeeze the entire star, all of its gas and plasma, down into the smallest possible space. Without anything to counteract it, gravity would cause the star to collapse in on itself in an instant. But fighting back against this inward crush is the second force, the tremendous outward pressure generated by the nuclear fusion in the star's core. The fusion of hydrogen into helium releases an incredible amount of energy, creating temperatures of millions of degrees. This intense heat generates a huge amount of pressure, pushing outwards from the core. This outward radiation pressure is what holds the star up, preventing gravity from winning. For most of a star's life, these two forces are perfectly balanced in a cosmic arm wrestle. Gravity pulls in and fusion pushes out. This delicate balance is what keeps the star stable, allowing it to shine steadily for eons. The star's core acts like a giant, self-regulating engine. If gravity were to momentarily squeeze the core a bit tighter, the pressure and temperature would increase. This would cause the fusion reactions to speed up, generating more energy and more outward pressure, which would then push back against gravity and cause the core to expand slightly. If the core were to expand too much, the temperature and pressure would drop, slowing down the fusion rate. This would reduce the outward pressure, allowing gravity to once again squeeze the core a little tighter. This self-correcting feedback loop maintains the star's stability throughout its long life. However, this balancing act can only last as long as the star has fuel to burn in its core. The primary fuel for this process is hydrogen. A star is essentially a giant ball of hydrogen, slowly converting it into helium. But the hydrogen supply is not infinite. Eventually, the star will start to run out of hydrogen in its core, the very fuel that has kept it stable and shining. When this happens, the delicate balance is broken. The outward push from fusion begins to weaken, and gravity, which never gets tired and never runs out, starts to gain the upper hand. The star's final dramatic chapters are about to begin. When a massive star exhausts its core hydrogen, it's the beginning of the end. With less hydrogen to fuse, the outward pressure drops. Gravity wins, and the core contracts and heats up. This ignites the hydrogen shell, causing the star's outer layers to swell dramatically, transforming it into a red supergiant. As the core contracts, it fuses helium into heavier elements like carbon and oxygen, releasing energy and temporarily halting the collapse. The star burns through fuel at an increasing rate, creating heavier elements in a layered core until it reaches iron. Fusing iron consumes energy, so when the core becomes an inert ball of iron, the star's engine has run out of fuel. With no outward pressure, the star faces its final violent demise. With an inert iron core at its center, the massive star has lost its final battle against gravity. The outward push from nuclear fusion has ceased completely. There is now nothing, absolutely nothing, to hold back the crushing weight of the star's outer layers. In less than a second, gravity wins in the most dramatic way imaginable. The iron core, which can be as massive as our sun but squeezed into a ball the size of the Earth, collapses catastrophically. It implodes at incredible speeds, reaching up to a quarter of the speed of light. All of that matter rushes inwards towards the center, squeezed into an ever smaller, ever denser space. This sudden, violent collapse of the core triggers a chain of events that results in one of the most spectacular explosions in the universe, a Type II supernova. As the core collapses, it becomes so dense that it can't be compressed any further. It essentially bounces back. This rebound sends a phenomenally powerful shockwave blasting outwards through the star's outer layers. This shockwave, combined with a massive flood of ghostly particles called neutrinos, rips the star apart. The outer layers are blasted into space with tremendous force, creating an expanding cloud of gas and dust enriched with all the heavy elements forged inside the star. For a few weeks, this single dying star can outshine its entire home galaxy, blazing with the light of billions of suns. It's a truly awesome spectacle, a final, glorious firework display. This explosion seeds the surrounding space with elements like carbon, oxygen, and iron, the very elements necessary for building planets and eventually life. The chair you are sitting on, the iron in your blood, the calcium in your bones, all of it was forged in the heart of a massive star and scattered across the galaxy by a supernova explosion long ago. We are, quite literally, made of stardust from these ancient cataclysmic events. But what about the remnant left behind at the center of this explosion? It all depends on how massive the original core was. If the core was relatively small, the collapse might be halted, forming an incredibly dense object called a neutron star. But if the core was massive enough, roughly more than 3 times the mass of our sun, then nothing in the known universe can stop the collapse. Not the pressure of electrons, not even the pressure of neutrons. Gravity is completely unopposed. The core continues to collapse forever, crushing all of that mass down into a single, infinitely dense point with zero volume. In that final, silent moment of ultimate collapse, a new black hole is born. We've witnessed the fiery birth of a black hole from a colossal star. Astronomers have discovered that black holes come in a range of sizes, from stellar mass black holes wandering through our galaxy to supermassive behemoths at the heart of nearly every galaxy. The most common are stellar mass black holes, direct descendants of massive stars. At the other end, we have the supermassive black holes, containing the mass of millions or even billions of suns. These giants don't form from the collapse of a single star. Their origin is one of the biggest unsolved mysteries. Astronomers have long predicted the existence of intermediate mass black holes. Understanding these different types helps us piece together how galaxies form and evolve. Let's look at stellar mass black holes. These form from the life cycle of massive stars. Imagine a star born with 25 times the mass of our sun. It explodes as a supernova, leaving behind a compact remnant, a brand new black hole. These black holes are scattered throughout galaxies, like stars. Astronomers have found them in our Milky Way, like Cygnus X1. It was identified by detecting X-rays from a nearby star. Gas forms a spinning accretion disk, heated to millions of degrees, glowing in X-ray light. X-ray telescopes spot this glow. By studying the companion star's motion, we calculate the mass of the unseen object. If that mass is more than 3 times our sun's, it's a black hole. Most stellar mass black holes are solitary. One technique involves gravitational microlensing. The black hole's gravity briefly brightens a background star. Now, let's talk about the heavyweights, supermassive black holes. These giants reside at the center of almost every large galaxy, including our Milky Way. They're gravitational anchors around which galaxies revolve. M87's black hole, imaged by the Event Horizon Telescope, weighs 6.5 billion times the mass of our Sun. Our own Sagittarius A star is much smaller. How did these black holes get so big? Did they grow by merging or form from gas clouds in the early universe? Scientists are working to unravel this mystery. We've met the little guys and the colossal giants, but what about what's in between? You'd expect to find intermediate mass black holes, or IMBHs, with masses between 100 and 100,000 times that of the Sun. But for decades, they remained stubbornly elusive. The most promising places to look for them are in the hearts of dense, ancient star clusters known as globular clusters, or in the centers of smaller dwarf galaxies. And finally, we have primordial black holes, not formed from collapsing stars at all. Instead, the theory suggests they could have been formed in the very first second after the Big Bang. These primordial black holes could come in a huge range of sizes. Some scientists have proposed that these ancient relics could be the mysterious dark matter that makes up about 85% of the matter in the universe, revealing the universe to be even stranger and more wonderful than we ever imagined. Imagine you're an astronaut approaching a black hole, an abyss in space where gravity reigns supreme. As you draw near, gravity's pull grows stronger, but the real threat is tidal forces. Your feet feel more gravity than your head, stretching you out in a process called spaghettification. For small black holes, you'd be torn apart long before reaching the edge. But with a supermassive black hole, you might actually cross the event horizon intact. Time itself warps to distant observers. You slow down and fade, never quite reaching the edge. Your ship's light reddens and dims, stretched by gravity, until you appear frozen at the brink. But for you, the journey continues into the unknown, where space and time twist beyond recognition. The black hole's edge is not a wall, but a point of no return, where the universe outside slips away. This is the threshold of the abyss, where the rules of reality begin to unravel. Inside your ship, time feels normal even as you cross the event horizon, the black hole's invisible boundary. There's no sign, no jolt, just a silent crossing into a region where escape is impossible. Space and time swap roles. Falling inward becomes as inevitable as moving forward in time. The singularity at the center is now your future. Every path leads there. Looking back, the universe shrinks to a bright, distorted circle. Ahead, only darkness. No signal, no light, no hope of return. Gravity's grip is absolute. You are now cut off, a traveler on a one-way journey to the heart of the black hole. The outside world can never know what happens next. Inside, the tidal forces intensify, stretching and compressing you into a stream of particles. At the center, the singularity awaits, a point where physics as we know it breaks down. Here, matter and information seem to vanish, defying the laws of quantum mechanics. This is the infamous information paradox. Does the black hole truly erase everything, or is there a hidden escape? Some theories suggest information leaks out as Hawking radiation, but no one knows for sure. The truth remains hidden, locked inside the most mysterious object in the universe. To solve this riddle, we need a new theory, one that unites gravity and quantum physics. Black holes aren't cosmic vacuum cleaners. They only threaten what gets too close. If our sun became a black hole, Earth would keep orbiting, just in darkness. When black holes collide, they send out gravitational waves, ripples in space-time we can now detect. The largest known black hole, TON 618, is 66 billion times the mass of our Sun, so big it could swallow multiple solar systems. These giants challenge our understanding of how anything can grow so massive. The idea of black holes dates back to John Michel in 1783, who imagined dark stars with gravity so strong even light couldn't escape. His insight was forgotten for a century, but it laid the groundwork for one of science's wildest discoveries. Curiosity, it turns out, is the real engine of cosmic exploration. Black holes answer some questions but raise even more. The information paradox, does information vanish forever, remains unsolved. How did supermassive black holes form so quickly after the Big Bang? What really lies at the center? A singularity, a fuzzball, a wormhole, or something stranger? Could dark matter be made of primordial black holes from the universe's earliest moments? These mysteries push the limits of physics and imagination. The search for answers continues, promising new discoveries and deeper questions. The universe's greatest secrets may still be waiting inside the abyss. After all this, you might be wondering why scientists are so obsessed with these dark, destructive objects that are so far away. Why do we spend so much time, money, and brain power trying to understand them? The answer is simple. Black holes are not just cosmic curiosities. They are the ultimate laboratory for testing the laws of physics under the most extreme conditions imaginable. They push our theories of gravity, space, time, and matter to their absolute breaking points. By studying these extremes, we learn about the fundamental rules that govern our entire universe. If our theories can survive the test of a black hole, we know we are on the right track. Furthermore, black holes are not just agents of destruction. They are crucial players in the grand cosmic story of creation and evolution. We now understand that supermassive black holes play a vital role in regulating the growth of their host galaxies. As they feed, they can blast out colossal jets of energy that can either trigger the formation of new stars or blow away the gas clouds, effectively shutting down star formation. Understanding this cosmic feedback loop is essential to understanding why galaxies, including our own Milky Way, look the way they do. The story of the stars is inextricably linked to the story of the giants that lurk in the galactic shadows. On a more philosophical level, our fascination with black holes stems from our innate human desire to explore the unknown. They represent the edge of our knowledge, the ultimate frontier. They challenge our intuition and force us to confront concepts that seem to belong more to science fiction than to reality. Warped time, inescapable abysses, and points of infinite density. Pushing against these boundaries is what drives science forward. Every new discovery about black holes, whether it's the first image of an event horizon or the first detection of gravitational waves, expands our understanding of what is possible and deepens our appreciation for the magnificent, weird, and wonderful cosmos we inhabit. So, the next time you look up at the night sky, past the streetlights and the familiar constellations, remember what's hiding out there in the dark. Remember the stellar ghosts, the wandering loners, and the supermassive giants holding entire galaxies in their gravitational grip. These are the universe's greatest mysteries, its most extreme environments, and its most powerful engines. They are the secret life of the cosmos, and we have only just begun to scratch the surface of their story. The journey into the abyss is far from over. In fact, it's just getting started, and that is a truly exciting thought.